friends, in this video we will look at the memory representation of a binary tree, and we will be discussing two types of representations. One is the representation using an array and the other is the representation using the linked representation. I will be discussing in this video only using array, and the linked representation I will discuss in the next video. So let us begin. So first of all, using an array, if I have a tree like this in which I have A, B, C, D, E, F, G nodes and I want to represent it using an array, then how I should be storing these numbers, these values in the tree into the array. There are many questions. That is, what should be the size of the array? Then how many nodes can be saved? What is a sparse tree? What is resizing is required or not? So all these questions I will be answering in this particular video. So first of all, we have to understand that for storing a tree of size 7 nodes, I require 7 spaces in the memory. And one thing we have to notice that the index 0 is never used in the tree representation. You can utilize this particular space for storing how many nodes are there in the representation, how many nodes are actually present in the binary tree. Like if I have 1, 2, 3, 4, 5, 6, 7 nodes, so I can store here a value of 7 to represent how many nodes are there are stored in the array. So in case one of the child is not there, suppose E is not there, then 6 nodes are stored. So we will place a value of 6 at the index 0. But for representing the node values, we will not make use of the 0 index. So always in a binary tree, the root will be at the index 1. So we can see here at index 1 we have A. Now all other addresses are derived from this main address of the root. So now for the address of the node B, which is the left child of the root, we have stored at the index of the parent into 2. So index of the parent is 1 multiplied by 2. So we store it at the position 2. So we can see here at position 2 we have B. Then where do we place the child C, which is the right child of the root? We store it at the index of the parent into 2 plus 1. So at third position we have the child C of the root A. Then where do we store the node D? We store node D, which is the left child, at 2 into 2, that is the index of the parent. B's index is 2, so 2 into 2 plus 4. This is the position of the D. And similarly for F, which is also the left child of node C's address is 3, so 3 into 2, 6. 6 is the position of F. Then for E, which is the right child of the node B, so 2 into 2, 2 is the address of the node B into 2 and plus 1, and we get the value of 5. So this 2 represents that it is a binary tree, and this index here represents the position of the parent. And similarly we have the storage for the G, and the G is stored, which is the right child of C, is stored at 3 into 2 plus 1, which is the 7th position. So I hope it is clear to you how the addresses are getting calculated. The left child is always at the index of the parent into 2, and the right child is always at the index of the parent into 2 plus 1. Now the question arises, how many spaces should I have in order to store a tree? So in this tree we see that there is the height of the tree is 2. How we have arrived at this height? This is the depth 0. The root is at the depth 0. Then B and C are at the depth 1. And D, E, F, G are at a depth of 2. So whatever is the maximum depth of the tree, that is the height of the tree. So the height of the tree is 2. So what we will do is, whatever is the height of the tree plus 1, and we will raise it to the power of 2, and that will be the position where we are going to. So if the height of the tree is 2, so 2 plus 1, 3, 2 raised to the power of 3 minus 1, so 7 locations are required. And how many nodes can be saved? 7 nodes can be saved. And how we have arrived at this? Height of the tree plus 1, and n, whatever is the height of the tree plus 1, that raised to the power of 2 minus 1. Now, what is a sparse tree? Sparse tree is, suppose this D is not there, F is not there, and G is not there, only E is there. So that in that case, some of the children are missing for a particular tree. But in the array, we have to declare for all possible children which are there. So whatever is the depth of the tree, maximum depth of the tree, according to that only we have to calculate, even if some of the nodes, some of the children are missing. And in case of a sparse tree, it leads to wastage of space. Suppose there are only 5 nodes in the tree, and I'm storing for a depth of 4 or 5. So in that case, it will lead to a lot of wastage. If your tree is skewed or some of the children are missing, in that case a lot of wastage will happen. And what if the size of the tree is going to grow beyond this array of size 8? In that case, we require resizing. We need to redeclare an array and reassign all the nodes to that particular array. So in case the size of the tree is going to increase, then also we are going to face a problem. That is why using an array, if you represent a tree, both if less nodes are there, it leads to memory wastage, and if more nodes are there, we require resizing. And therefore, this method is used only when the size of the tree is somewhat fixed. Otherwise, we make use of the linked representation, which I will be discussing in the next video. Thank you very much for watching.